Welcome to this lecture series in real analysis. We have started our discussion on the exponential function, and in this lecture we'll prove some properties of it. So what was our definition? The exponential function was defined as any function f from reals to reals, which is its own derivative, and a non-triviality condition which states that it takes the value 1 at 0. So why am I calling it a non-triviality condition? Well, we saw that if we had assumed, for instance, that f0 is 0, then such a function would necessarily be the identically 0 function, meaning there is only one function which satisfies this condition, that it is its own derivative and it takes the value 0 at 0. Right? So this non-triviality condition was imposed, and we saw that there is at most one such function. In fact, that was just by using the fact that if you had asked for vanishing at 0, you get the identically 0 function. That implied the uniqueness of the exponential function, and the existence was proven by explicitly constructing it, though we were inspired by Taylor's theorem when we were proving existence. We were inspired by Taylor's theorem when we wrote down that infinite series. Okay, so this was one of the theorems or one of the lemmas that we proved. What we just kind of stated. Okay, and this was the explicit description of the exponential function in terms of an infinite series or as an infinite series. Okay, some problems for practice, and now let us get started. Right, so the first property is what I am calling positivity. It states that the exponential function is always positive in its entire domain. So what is this notation? This is same as x of x, just a different notation. This is the value of the exponential function at x. So we are saying the exponential function is always positive. Why is that? Well, suppose it vanishes somewhere. If it vanishes somewhere, then we claim that it will vanish everywhere. Why is that? Well, in the previous lecture we saw that if it vanishes at 0, a function that is its own derivative, if it vanishes at 0, it will vanish everywhere. That's what we proved in the previous lecture. The same proof will show you that if it vanishes anywhere, it will vanish everywhere. There is no sanctity to 0. Okay, so I leave that part as an exercise. It's a direct mimicry, or a direct mimicry of that proof will lead you to this fact. So the exponential function cannot vanish anywhere. What about taking negative values? Well, if the exponential function takes negative value somewhere, it will have to vanish somewhere. Why? Because the exponential function takes positive value at 0. Right? So it takes positive value at 0. If it is vanishing anywhere, since the exponential function is continuous, in fact it is differentiable, since it is continuous, it will have to vanish somewhere by the intermediate value theorem. Right? It is taking positive value somewhere. If it takes negative value somewhere, then it has to vanish somewhere. But then again, the same argument kicks in. It will show that the exponential function vanishes everywhere, which is of course not true. So that proves this. And so the second claim or second aspect of this property is that the exponential function is strictly greater than 1 whenever x is strictly greater than 0. So why is that? Well, again, let me not write anything down. So the exponential function takes the value 1 at the origin. Suppose the exponential function is violating this line, then there is some positive x where the exponential function is either equal to 1 or less than 1. Suppose it is equal to 1 for some positive x, then we see that the exponential function is taking the same value at two different points, namely at the origin and at this point that we just talked about. So if it is taking the same value at two different points, then by Rolle's theorem, the derivative of the exponential function must vanish somewhere. but the derivative of the exponential function is same as the exponential function. So that shows that the exponential function vanishes somewhere. But again, if the exponential function vanishes anywhere, it will have to vanish everywhere because the exponential function is its own derivative. Right? So therefore, it cannot take the value 1 anywhere on the right side of the origin, or even on the left side of the origin. In this, the same argument shows. Similarly, it cannot be less than 1 on the right side of the origin, because if it were less than 1, then applying Rolle's theorem, or whatever, Lagrange's mean value theorem, we see that the slope, or rather the derivative of the exponential function somewhere in between will have to be negative. Right? All I'm saying is, suppose it takes negative value somewhere. Not negative. Suppose it takes a value less than 1 somewhere. Right? So then by Lagrange, there is some point, call it P, between the origin and this point where the value is less than 1, such that the exponential function has same slope as this line, but this line has negative slope. So that means the derivative of the exponential function will be negative somewhere. But the derivative of the exponential function is same as the exponential function, so that would mean the exponential function is negative somewhere, but we have already argued that the exponential function is not negative anywhere. It is in fact positive everywhere. So that's it. I don't want to write this down. I have said it in words, and it's a fairly simple piece of reasoning. We just need Rolle's theorem and Lagrange's theorem. Okay, so this shows that the exponential function is always positive and always greater than 1 on the right side of the origin. Okay. So the next is the homomorphism property. This is interesting. So it says that if you take the exponential of a plus b, you get product of the exponentials. So in the other notation, we can express the same thing as exp of a plus b is xA times xb. Right? And this terminology comes from group theory. Do not worry about this particular word. It's just a word so that we can remember this property by. Okay, so again, even in the previous property, we could have just used the infinite series of the exponential function and maybe argued at least the fact that the exponential function is greater than 1 on the right side of the origin would have been pretty easy via that infinite series. But I do not want to use the infinite series. I just want to use the pristine definition of the exponential function in order to argue these things. And what is the pristine definition? The definition is that it is a function. It is a function which is its own derivative, and it takes the value 1 at the origin. Right? And the fact that it exists required us to construct it by an infinite series. That's a different matter. But as far as possible, we will try to only use the pristine definition. So why is this? Okay. So here is the proof. Fix A. Okay. And we want to show that this is the case. Yeah. So, right. So define a function f as f of x equals e to the a plus x divided by e to the a. And this is legitimate because we already showed that e to the a is positive. So when I say e to the a, I just mean the exponential of a, the exponential function fed a. I'm just reading it as e to the a. Okay? So the exponential of a plus x divided by the exponential of a, that is what f of x is. So what do we want to show? If we want to show this, we want to show that this is same as exp of x. Right? That's what we want to show. So we just want to show that this is same as the exponential function. But to show that this is the exponential function, we just need to show that it satisfies the properties of the exponential function. What are the defining properties? Two things. One is that it should be its own derivative, and the second is that it should take the value 1 at 0. The second property is clear. If you feed 0 in place of x, you see that this is just e to the a divided by e to the a, which is 1. So the second property is clear. What about the first property? Well, that is also clear immediately by the chain rule of derivative or whatever. So by the chain rule, f prime x is nothing but the derivative of the exponential function at a plus x divided by x of x, x of a. Yeah, that's it. That's what it is. Right? So I haven't done anything. I mean, just let me rewrite this in this other notation, which might make it a little more clear what I've done. I've just used the chain rule of derivatives. Right? But the exponential function is its own derivative. So this is equal to x of a plus x divided by x of a, which is the definition of f of x. So f prime x is same as fx, therefore f is its own derivative, and hence f is the exponential function because the second property we already verified. So this is the exponential function, and hence what we see is that x of a plus x divided by x of a equals x of x, which implies what we wanted to prove. This is true for all x. And now you can just put b in place of x to make it look more like what is written here. Okay, so that proves this very nice homomorphism property. Okay. The next is monotonicity. So we want to show that the exponential function is monotonically increasing. Well, we just showed, or maybe property 1 showed that the exponential function is always positive. Therefore, the derivative of the exponential function is also always positive because the exponential function is its own derivative. And if you have a function which is its own, if you have a differentiable function which is always having positive derivative, then that function is strictly increasing, right? You can see that using the fundamental theorem of calculus also, because let's just maybe go from a to b where a is less than b. Then this is same as x b minus x a, right? This is from the fundamental theorem of calculus, but this is always positive, so this is a positive quantity, and hence this is a positive quantity, which shows that if a less than b, then x of a is less than x of b. So it shows monotonically increasing, but we didn't really need to use the fundamental theorem of calculus. We could have, we proved this property that having positive derivative implies monotonically increasing. That is, you can prove it using Lagrange. Anyway, so that's another property. Next is a little estimate, a small estimate that we have here. So x of x is at least 1 plus x whenever x is non-negative. In fact, you don't even need this. This is true for all x. This thing is true for all x. But let's just prove it for non-negative x because that is all that we need here. Maybe I'll leave as an exercise for you to show that this happens for all x. So why is this? Well, here you can use the fundamental theorem of calculus. That will be the shortest way to do it. So integral from 0 to x, take x positive, integral of the derivative of the exponential function is equal to x of x minus x of 0 by the fundamental theorem of calculus, but x of 0 is 1, right? But we also know that the derivative of the exponential function is the exponential function by definition of the exponential function. So we have this, and hence we have x of x is 1 plus this integral, right? I've just shuffled things around and written it like this. But recall that we know that x of x is at least 1 for all x non-negative. This was one of the properties that we saw. Therefore, x of x is greater than equal to 1 plus the integral of the constant function 1 from 0 to x, which is equal to 1 plus x. So the exponential function is at least 1 plus x for all x positive, but I encourage you to prove it for every x. Okay? And therefore, this is now clear. If you have this, clearly this has to hold, right? The exponential function grows without bound, and that is what the statement is. What about the other one? Why is it true that if you take, if you put smaller and smaller values as inputs to the exponential function, you are you're going closer and closer to 0. You'll always be positive because the exponential function is always positive, but we are saying that it will come as close to 0 as you like. Why is that? Well, you use the homomorphism property. So if x is very large, then we know that x of x minus x, which I will write this way, is equal to x of x times x of minus x. Think of x as a very large positive number. Then, well, what is the left side? The left side is 1. Because x minus x is 0, so the left side is 1. So this is equal to x of x times x of minus x. Now, this grows without bound because we already showed that. So this has to come down. This has to become as small as you like. And that's it. And that proves the other part. Right? So that's it. We have proven these two properties. All right. Now, finally, what is the image of the exponential function? So we claim that the exponential function, first of all, is a bijective function onto the set of all the positive reals. So this is the entire fact about the range. The range or the image of the exponential function is precisely the positive reals, and in fact, it bijects onto that. The exponential function maps the real numbers bijectively onto the set of all the positive reals. Okay, so why is that? Well, first of all, the exponential function is injective. Why is it injective? Well, if it were not injective, then it would take the same value at two different points. But then by Rolle's theorem, the derivative of the exponential function would vanish somewhere. But the derivative of the exponential function is the exponential function. Hence, the exponential function would vanish somewhere. But then the exponential function would be 0 everywhere. That's it. So this is a consequence of Rolle's theorem. In fact, this kind of reasoning we saw when we were proving positivity. So exponential function is injective. And now why is it so that it will achieve every positive value? We know that it is contained in the positive reals. The image of the exponential function is contained in the positive reals because of the positivity property. The exponential function is always positive. Why is it that it achieves all positive values? Well, because of the previous property. We know that the limit, this expression is infinite, and the other one is 0. And the continuity of the exponential function now combined with these two things shows that all positive reals will be in the image of the exponential function. Just use the intermediate value theorem. Okay, so that's very nice. Lastly, the growth rate. So what are we saying? We are saying fix some positive integer n. Then the growth of the, in the numerator you have a polynomial. In fact, it's a monomial. We are saying the growth of the monomial, any monomial, fix an n, you get a monomial. The growth of the monomial is nothing compared to the exponential function. The exponential function beats any monomial and hence any polynomial. I could have written that let p be a polynomial, then the exponential function beats that polynomial. Okay, so why is that? Well, if you want to not use the formula for the exponential function, you can just use L'Hopital's rule. This is an infinity by infinity form. As x goes to infinity, this is infinity as well as the lower one. You differentiate once, this will not budge, while in the numerator you will have a smaller value of n. You keep applying L'Hopital's rule, at some point you will get 1 in the numerator and the exponential function in the denominator. Well, not quite. In the numerator you will see n factorial or some such thing, because every time you differentiate, this n kind of comes down and becomes a factor. But anyway, there will be some constant on the numerator, and the exponential function will be there in the denominator, and therefore you will be able to show this. But perhaps the easiest way to do this is to show that, or use the fact that the exponential function is at least x to the n plus 1 divided by n plus 1 factorial, whenever x is non-negative, immediately by the infinite series description of the exponential function. Once you write this, this should be now obvious. In the denominator, you'll have a polynomial or a monomial of higher degree. Monomial of higher degree, while in the numerator you have a polynomial of lower degree. So that's it. I mean, that does the job. So the exponential function beats every polynomial. It's a very fast growing function. And now let me wrap up things by just making the diagram or a graph of the exponential function. It sort of looks like this. Can't do a very good job, but it sort of looks like this. Very fast growing function. Okay. Yeah, so I think that's it. Right, so with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.